Hey, everybody. Hope everything's going well for you. We're here on day 18. I'm doing it a little earlier in the day just because I got it done pretty quick. I imagine it'll be a quick day. If you've done previous days, you can say to yourself, oh, I can just reuse a lot of code. I tried to do a couple things to kind of show off some differences in the way things works. But anyway, let's just get started. We'll talk about it, and you'll see why it was pretty easy. So it's called RAM Run, and the idea is you're now inside a computer, and you're like in a block of memory, and every nanosecond, like these uh this like program that's running is corrupting bytes and making it so you can't traverse those bytes is maybe the list of it. And what he gives you is a list of which bytes will fall in what order they do it. So they all fall once every nanosecond is the way that it's described, right? So can you imagine, again, you're doing a grid. You can imagine you have a grid, and every nanosecond, initially it's empty, but every nanosecond, one byte is going to be corrupted, and those become like your blocks or walls that you can't get through. Um, and so here's like a big grid for a test case, and in the test case, they want you to do the track the first 12 bytes. So they say after the first 12 bytes have fallen, it looks like this, right? So here's the graph that it looks like after the first 12. And then it says, and I actually misunderstood this for a little bit. Essentially, what it wants you to do is now from the beginning, the start, which is up here at the top, to the end, can you find the shortest path after 12 steps? It's different for the input. The input is much larger, like the graph is much larger. Um, the number of steps you want to take before starting is larger, like it's 1024. But the idea is the same: is you have some grid, and you're going to start up at the top left and try and get to the bottom right in the shortest path. The thing that I had confused is I thought you were still dropping it. So like if this is the state at 12 and I'm right here, if I move down here, it's now 13 nanoseconds, and another block should drop. That's what I was thinking it should do, but that is not the case. You're literally just take the first 12 points that you're given as your input and make a grid like this, and then find the shortest path through it. That's all it's asking you to do for part one. So again, if you've been through the days before, this is clearly find the shortest path, and it's Dijkstra's, right? You're literally just going to do Dijkstra's on your path, find the shortest path, and boom, you're done. Okay? So let's actually just look at the code. There's not much to it. Again, I used a point. So you can see here, I just, have my parse using nom, nothing really different. I did change the neighbors function. I think you've seen before where I've done like the point just returns all of the possible points, and then we filter it later. I tried to do some generic programming here where we say, if you give me some function f like this, that if you where the function is, I'll give you a point, you give me a bool, I'll filter it for you. So now that this point function, it doesn't know about the grid or the graph or what's going on, but I can give it this filter function, and then it will know enough to infer whether or not to include it in the list. So that's all that really changed here is, and I'm doing it this way. I'm using the list of like directions, or I'm using just the list of these different integer values as opposed to like having directions and doing the mutation. I thought I'd just show, here's another way to do it. I think we've seen this before in other reviews. So anyway, that's definitely one way to do it, right? Anyway, so that's all that really changes. I'm doing some generic programming here. If you're new to Rust and you maybe haven't tried any of this stuff, it doesn't hurt to like read the Rust book and see what it's saying. But this is just like higher order stuff where say, give me some function that meets this criteria, or that has this signature is maybe what I should say. And then I'll call that function through my filter. and then that will give me the list. You'll see them in a minute. But anyway, so here's some setup stuff, and then here's me parsing it again with nom. I don't know if I said this or not, but you probably don't need to do nom for this small data set. Anyway, but then I basically just do Dijkstra's. And before I show you all this code, I'll show you Dijkstra's algorithm, the way it works. Again, I did do this with some generics. So, and this is also a day that I wouldn't feel bad if someone said, oh, I already did Dijkstra's, I'm just going to use the pathfinding. That's totally fine. But here's my state. I am going to show you the difference between, at least for this problem, A star and Dijkstra's. It turned out not to be a big difference. You can see here down below, not a lot changed. But you can see anyway. So my state now is not just the node and the cost, but also some heuristic function, right? So I'm going to and again I used generics here to define the node type. So this, I could technically copy this code and use it as a Dijkstra thing for anything. But anyway, the essence is I need some cost and heuristic function. For Dijkstra's, I'm sure I've said this in previous videos, the difference between A star and Dijkstra is you just add the heuristic to the cost and hope that better it should better inform you on how to get there faster. And so you visit less nodes as you're branching, because you prefer nodes that are getting you there faster based on this heuristic. So what does that change? Well, it's really just changes this part right here for the A star algorithm. Is we say we're not just comparing the costs, we're comparing the cost plus the heuristic, and the smaller of the two of those should be the ones that we prefer, right? So we add the heuristic to the cost and just compare it to the other one is what we're doing here. Again, we do it in reverse because we're going to use a min heap, and so we want the smallest one to be on top. None of this really changes. Here's the Dijkstra itself. Again, I'm using like templating here or generics. So I say, you give me some start node and a successors function, which looks like this, where I'll give you the node and you give me the neighbors and the cost to get to that neighbor. In our case, it's only one. And you give me a success function that tells me whether we've reached the end, and a heuristic function which tells me, what is the heuristic of this particular node. Then I will run Dijkstra's for you. And again, I'm not going to go over this Dijkstra's very much because we've already done it before. But the general idea is you're slowly walking through this like frontier of nodes that you want to visit, but you're preferring nodes that have a lower cost to get there. And so eventually you reach the end of it, and now you've found the shortest path because you've always kind of traversed the path with the least cost. And the heuristic, again, can help inform that, right? If it, say there's two nodes of like equal cost, but the heuristic says this one should be faster, it will prefer to use that one. And that's, again, the difference between A star and Dijkstra's. How, just a word of warning, if you've never done A star before, you should definitely look it up. Doing this incorrectly will ruin the algorithm. It will actually make it wrong. It's better for you to not use a heuristic than to use a bad one. So make sure you're using a correct one. Anyway, so what does Dijkstra's do? We basically just keep looping through the frontier until we found, our goal, right? Our success returns true. Otherwise, we check if we've seen it before and if there's a better path. If not, we insert it so we don't have to visit this again. And then we just go through all of our neighbors and add them to our frontier to visit, right? And this is a heap, and when we've made it a min heap because of the way we're sorting. So we're adding on all these neighbors, but we may not actually visit them all. Okay. And so that's it. One notable thing for part 2, I don't know if I mentioned this before. If we've gone through all the nodes, right? We've gone through all the neighbors and visited all of them. Like imagine the case where we say, hey, what's the shortest path? But like these two nodes were, this node and this node was blocked off, and there's no way for me to get there. It should return none, right? And so that's what happens here. So if we go through the whole graph and we never reach the endpoint, then we return none. Okay. So given all that, I know I blew through that a little bit. You're welcome to look at it and ask questions in the comments. Happy to answer them. What do? I just need to create those functions, right? So how do I determine if I'm successful? It's where the point is the end, right? So if I ever reach the end, I'm successful. And then what is my successor's function? Um, well, I just can call that neighbor's function up above, or neighbor's method up above, I guess. And then here is the function I give it. I say for that point, p has to be in bounds. That's what these checks are, and it can't be on my list of corruptions, right? So if like I've corrupted some number of bytes, in this case it's 1024, I grab that first 1024 and make sure that p is not in there. You could optimize this by turning this into a hash set. In fact, I don't know, do you want to do that right now? Corruptions. Cloned.collect. I actually don't know how much this will speed it up. It probably won't speed it up anything. Oh, it actually does. Okay. Definitely worth doing then. Yeah. Okay, that definitely does speed it up. So you can see here is, where did I do this? Yeah. So here's our successor function again. But that really doesn't change anything, right? I'm basically just saying, here's the function for my neighbors. And so this is going to find me all of the valid neighbors. And so as long as I'm not in this corrupted list and I'm within bounds, then that is one of my neighbors. And so, and then I just map those and include a one, because we're always stepping one. The cost of every step is one, and I can return those values. And so there's my successor function. So again, I have a successful function that tells me if I've reached the end. I have a successors function that tells me if I've uh, tells me what the neighbors are. And then here's my heuristic function. I'm just doing Manhattan distance, right? So I'm just saying, how far am I from the end? And I just calculate that distance. And so the idea is, imagine yourself on a grid. If you're like right here, you'd prefer to go nodes that are this way as opposed to preferring to go nodes that are this way. Okay. And so it will just try those things before it tries other ones. And then I just run Dijkstra's both with and without the heuristic, right? So that's what this is here. I run my Dijkstra's algorithm with the heuristic. So this is the A star one. And if I find something, I print it out. Otherwise, I do this. This one is actually, I could do this in a match, I guess. Should we do that really quick? I did a let sum, and I know, well, everyone has different opinions on that. It didn't quite get it right. I'm just gonna. So, what is the difference between using A star and Dijkstra? It's just the heuristic is 0, right? So that's all I'm gonna do here for this. And let's see, Did it change all these? It did, yeah. A star. Okay, so now I'm using match statements with which some people prefer. If let is also okay. But because I was doing the else, it kind of felt like, oh, maybe it's worthwhile to just do those. Um, anyway, so that's all part one is. And so just to show you the difference between Dijkstra's and A star, all I've done is between the two calls is I actually return the Manhattan distance here, or I give it the Manhattan heuristic here. Otherwise, I just have it return 1 down here. And so this is like A star with a heuristic. This is A star with a 0, which is Dijkstra's. Okay. And so you can see here, I get the same answer. They run in about the same time. This one's slightly slower. I think this is well within variance, though. But you can see it's like some small percentage, like maybe 1% fewer nodes are visited. Again, that's not a big change. There's been days before, or I've seen like problems before where A star is actually really helpful. And it just has to do with, if you think about, if there's a lot of branching and it's like it branches really wide, but you know that trying to stay in the middle is more helpful. That's where A star really comes to shine, right? And so in this case, it turned out not to be it, but I thought I would just show you the difference and show you how it can help. Again, as a word of warning, if you ever use A star and it's like you're not getting the results you expect, check your heuristic function, because if your heuristic function is actually wrong, it will give you wrong results, right? And so you just want to be careful of that. Okay, part 2. What does part 2 say? It says, okay, great, you found this minimum solution. But what happens if you keep like falling blocks? What happens if blocks keep falling, or sorry, corrupted blocks keep falling? At what point does it become impossible to reach the end? Right? So you can see here it says after dropping block 6-1, it's now impassable, right? You start right here and you go to here and you stop right here. There's no way for you to get from here to here anymore. And that's the question it's asking you. So I actually don't know if there's a faster way to solve this. I'll show you how I solved it. And basically it's just brute force using par iter, and it returns really quickly. So I was like, okay, well, that's probably enough. We'll look online and see if there's like better solutions, and maybe we can even try them if I have time. But the gist of it is like all you really need to do is, can you find the point at which the graph becomes incompletable, and like that's what you're trying to do. Okay, again, you're doing it with a much larger graph. There's like several thousand of them, but the idea is just how do you know when it's incomplete, when you can't finish the graph? And so you can actually see that's just what I do here is I say find the first one. And notably, what made this really cool was rayon, doing the par iter. I can do find map first, which returns the first value that returns a none value, which makes this really easy, right? Because then I can literally just say, okay, I need to modify my successor function a little bit, but otherwise I can otherwise I just run Dijkstra's on the successor function, but with a different list of corruptions, if that makes sense. And then if there's ever some point where I don't have a solution, that's where the corruption was dropped that caused it to fail, if that makes sense. There is an off by 1 error there. I'll show you in a minute. But I actually want to go change this again to this right here. See if it speeds it up even more. I don't know if it will because you're building it each time. Maybe I build the initial one here. No, that's not going to work. I'm not going to be able to share it. So I need to build it here. And I do it to I. And then I do that. I don't know how much, if it will. Oh, it does. It speeds it up quite significantly. Okay. So building the hash set versus checking the list is definitely faster. Again, these are just milliseconds, but definitely is faster. Okay. So what, again, my start and my success functions don't change, and I'm not using the heuristic. I guess I could try it with the heuristic and see if it helps. I don't imagine it will because not much changed. I mean, it's negligible, the changes. It actually is. Oh, no, there's a good one. Anyway, I don't know if it helps you that much. But the idea is I'm just going to loop through each iteration of the list of corruptions until I find one that doesn't give me a result. That's all I'm doing right here. And so the only thing that changes from part one is I'm now going to test all of the cases where I'm going to increment, I'm going to add an additional corruption to the map, and then that alters what my successors function looks like. And then I just run Dijkstra's on it. You'll notice it's in reverse here. And why is it in reverse is because if I find one, that's not the one that I want to return as the result. It's when I don't find one, that's the one I want to return as the result to this. So that's what I'm doing there. So I'm finding the first corruption that prevents us from reaching the endpoint. And again, so like if you think about it, each of these take about 1 millisecond. If I have to consult like 5,000 of them, that's 5 seconds, right? That's a lot. I actually think there's only like 3,000 of them or whatever. So you probably, a max time of 3 seconds. That's probably still solvable. Okay, you don't have to use the par iter, but I thought I'd try that to show you how this is one of the optimizations you can do. Because at least for my solution, because you're just literally like brute forcing the part two, using the par iter helps here. Okay, so once I found that, that's my answer, and I just returned that corruption that caused it. That's what it wants you to return, is this XY value here to get to your answer right. And I did have an off by 1 error here. I thought I'd mention that. At first I thought, oh, I should just return corruption I, but I think the way that it's worded and the way it's if you think about it, is like you move and then it drops, is like what it's telling you, is like it happens within the same nanosecond. And so you're actually, you drop it, but you're actually interested in after you drop the next one, it fails, but it's the previous one that caused it, if that makes sense. And so I think that's why you get this off by 1. Or I just could have no idea what I'm doing. So if you know, if you got an off by 1 too, or you know why I'm getting an off by 1 and I need to do I minus 1, let me know. Oh, is it because of the 0 verse 1 thing? I actually don't know what it is. I'm not going to think about too much of it. But anyway, that's part 2. So again, a relatively easy day if you've done previous days. I think even if you brute force this without par iter, you still get the answer in a few seconds, and you probably feel okay about yourself and don't have to worry about it. This is also a day where I don't feel bad. Notice I'm using this thing right here. I'm pretty sure I could literally like drop and replace the pathfinding crate for these Dijkstra's calls and this A star call. I could probably just like drop and replace them relatively easily to do this. So if this is a day where you felt like, oh, I'm just going to use an existing pathfinding algorithm, that was probably a good way to do it too, right? I don't have a problem with that. So anyway, there's day 1 and 2 for 18. Now maybe let's look at some code. Day 18, I was excited for a minute. List of numbers 2D. Yeah, we do. It is another grid, right? We're doing another grid. It looks like points, and maybe you think you're okay, but you are actually not okay. BFS brute force solution. I guess I don't know how big. It's a 70 by 70 grid. You probably don't even need Dijkstra's. You could probably just do a BFS and solve it. It's definitely going to be slower, but you could. That's it. That was part 2. No gravity or bytes falling as you walk. Was just a for loop. Yeah. So I actually had this issue, the bytes falling thing. I think I said that in part 1, right? I thought it was like, oh, as you're walking, bytes start falling, and now you have to figure out how to get through that as the bytes are falling. and that kind of changed the way it worked. I was trying to think of like how you'd solve that, because like if you think about the way Dijkstra's works, and you're finding nodes, you'd also have to track like the state of those nodes, like, or the state of the graph in those nodes, because the shortest path differs as you're moving. It's like the graph itself is changing as you're traversing. Um, Maybe it still works because like at any moment you're only really just interested in a single node and its neighbors, and you just have to decide whether that node is available based on whether or not you, or what your current corruption list is based on the number of nanoseconds or steps you've taken. So anyway, you could probably still figure it out, but it was a relatively simple day if you just did a for loop, which is what I did, right? I essentially did a for loop. Wait, didn't we just see that one? Okay, yeah, we did see this one. What the? Reading was hard today, 70 by 77. Oh, this was a thing. Uh it it says right here it goes from 0 to 70. Like, and so I did have to think about that a second. It doesn't mean the cap is 70. It means that like there's a total of 71, I guess is the way to describe it. So that's kind of funny, yeah. Only process the first bytes fallen to base bytes fall. No gravity simulation. Okay. Yeah, we have had days, and we may have them still this year, where I don't know. Do you remember like the Tetris one where you have to deal with gravity and stuff like that? Um, the This was definitely an easier day 2, I think, on average than most. So copy paste day 16 and remove direction stuff. Copy paste day 16 and make direction changes. Cost 0. Oh, this is the reindeer one, right? Yeah, that would totally work. If you've already done the pathfinding and you just like change the direction cost to 0, that totally works. Awesome. Perfect. Raining bytes visualization. Yeah, you probably can visualize finding the graphs of all the points and like the point at which it fails. This is not hard. Again, it doesn't take, the grid is small enough that it shouldn't be too hard to like find, you know, to find an optimal solution for like each step of the 3000. That's why I think the brute force one's probably okay. You know what I mean? Anyway, if it ain't broke, don't fix it. Binary searching for the first failure. Oh, that could speed things up too. I just did it in a for loop. So what is a binary search? Imagine you have your, I kind of want to draw it. If you've never done a binary search before, maybe you have, but this would be a good one. I should say my plans are kind of to try and do some like recaps or like addendums to some of these things. And so this might be a good way to fix this one. So imagine this is our list of corruptions, and forgive my drawing. And so we know that like these ones are our start ones. And we know that at some point in here, there is a failure, right? There's something that's going to cause the algorithm to not find. So the way I did it was very linearly, right? I just was like, and went this way using the par iter. I guess I don't know exactly how the par iter works. Like maybe it did this for me. But you can also do a binary search. And the way that works is you test this middle value right here, say, and you say, does this cause a failure? And if it doesn't, you know that the failure now is on this half of the issue versus this half, right? You know that all of these succeeded because this one succeeded, and so but the failure is somewhere in here. So now you consult the middle one in here, right? So we're going to now ignore all of these. and you consult this one, and let's say that it does fail. Well, now you know that the failure point is somewhere in here, right? And so you can ignore these ones. And so now you're going to test these, and you basically just keep doing that until you get the exact failure point. You'll get eventually you'll like it's called a binary search because you're breaking your state space in half each time, right? You start with some big state space, and then it's like half as big, and then it's like half as big until it's one, and now you found the exact moment where the failure occurs. So that is very cool. But yeah, brute forcing I think was pretty cool enough. Uh, it would be fun to do a binary search though, so maybe we'll do that in one of our reviews. Day 16 and day 18 algorithms and data structures class feels like it was a millennia ago. Yeah. Just I don't have a problem with using the pathfinding algorithm or whatever language you're using. Um, use their libraries. They probably already exist, or just look it up. That could be the fun thing about finding and solving these. Is hey, how does that thing work? If you're really into puzzle solving, these will come up a lot, and so it doesn't hurt to try them. I present to you the off by one error support group. At part one, I've counted the start steps as a step. At part two, I've returned the last good coordinate. Yeah. Okay. That's okay. Apparently, I was not the only one that was in that. I first returned the step number, then I returned the next falling rock after it was blocked. Finally, I also had the coordinates swapped. Oh no. Poor guy. That's a lot. My grid was 69 by 69 because my bounds checks was less than instead of less than cost me 10 minutes. Oh no. Yeah, I had an off by one too. So there you go. Yeah, my first submission failed and it was off by one. I actually the way I fixed it was I printed out all the different ones it was finding, and then saw that in the test case I was all like, oh, it's the previous one. LOL. So day 16 but easier. Yeah, it was easier. Day 18 feels easier ish. So oh, this is cool. He calculated how fast you need to run to escape the memory. It's 150 megabits per second. How's that 1.2 gigabits? Until we meet again. Ha ha ha. Did anyone ever watch He-Man? Stuff like that? Am I too old? Can you move while bytes are falling? Or you can move while. These are good questions to solve. Ask. Again, this is the one that I was trying to solve to begin with, and I was not getting the right answer. I think I was in the test case, I was getting no. I don't remember. Maybe I wasn't getting no solution, but I was definitely not getting the right answer for the test case, and I was like really bugged. Um, so that's a good question to ask. Is like as the bytes are falling. Spinning 30 seconds, doing a for loop over a few thousand steps takes 20 milliseconds each. Spinning 5 minutes off by one area binary. There you go. Okay. Okay, so some other people, many people did binary search. That totally worked. It didn't even occur to me. I probably should have added that to my like check. Poor predictable Bart always uses brute force. Good old brute force. Nothing beats that. I mean, it works. It works. A star, yeah. Again, we looked at it. You probably don't need to use A star for this, but it does allow you some optimizations. Uh, okay, let's just look at some solutions and then we'll be done. Again, today's was relatively easy, so I don't think there's a lot of craziness to it. Dijkstra's, brute forces. Oh, this is a cool idea that I didn't think about. So you in previous days we've talked about one of the cool things of Dijkstra's is you can actually return the path that you took as opposed to just saying what is the shortest path. And so what he's saying is if you found the shortest path, you just need to find a node that interferes with it. Does that actually work? Because your shortest path can actually change, right? I mean, it can't change in this one. Maybe the puzzle is just lined up that way. Like, uh, say your shortest path is something like that, and like then these, but like, you go here, and then this thing blocks down, and so now your shortest path is to go this way, and then this thing blocks down, and now your shortest path is to go this way. Like, you actually change the shortest path. So I'm curious if that actually works. Maybe it just works in the special cases, but not the general cases. Which is okay. Again, I've said this before. If you're solving the puzzle and you solve the puzzle, that's fine. Let me just make sure I understand that. Basically, when you do Dijkstras, you can also determine the shortest path that was taken and store them in a set. And as you iterate through your test data, if the indices don't interfere with your current known path, you can skip it if and move on to the next until you find one that does. Then simply recalculate and repeat. Perfect. Yeah, that solves the problem I was thinking about. I didn't finish reading their thing, so that's perfect, right? Is like you get your path from Dijkstra's, then you iterate through all the values until it closes it off, and then you recalculate there. So you don't have to recalculate Dijkstra every time. You only recalculate it at the points where it matters, right? So again, uh, like how does it look here? You have some list, and like here's the start, and you know Dijkstra's works here, and that gives you some path, right? So you now have this path that works. Well, now you can just iterate through these values and check if it's on the path. So is this one on the path? No. Is this one on the path? No. Is this one on the path? No. Is this one on the path? Yes, it's on the path. So now we just take this and we recalculate Dijkstra, and Dijkstra will give us like a new path through the maze. And then we just keep doing the same thing until we get to one where it's like, no, it doesn't. And we recalculate Dijkstra again, and Dijkstra says there's no solution, right? And then we know that this is the one, right? So the idea is between the thousands of ones that you're processing, maybe only two of them interfere with your path, and it's only until you get to this one that it like fully interferes with all of your paths, and now there's no solution. That's cool because the intuition here is that like many of these drops may not change your shortest path, and it's only when your shortest path changes that you need to be interested in it. So that's a great solution. I had not thought of that. Partly because the brute force worked. This is the kind of a funny thing. I don't know if you do this, but I tend to take the approach of try it with brute force, see if it works, and if it doesn't, then optimize. Because I've seen too many times where people over optimize, is I guess is what it is. So I try and stick to the don't over optimize until you need to. Um, that being said, I use Dijkstra's here, and it's potentially small enough that you could just not use Dijkstra's. Dijkstra's is such an easy algorithm, though, that maybe it doesn't matter. Who said you can't brute force part 2? No one. You definitely should be able to. So he has this. He calls this build graph function on the list of bytes that have filled. What does this build graph do? Okay, he's creating edges, but he's ignoring the ones that are not in the grid or not in the bytes, right? I guess it's not ignoring them. He's marking them as like a wall. Okay, yeah, so literally just brute forcing it. I think it totally works. Reused parts of day 10. What was day 10? Was it another Dijkstra's? I actually don't remember how I solved this now. I think I just did BFS for this one. Open folder. Open file. Because they're different. Yeah, I just use a DFS. And then this is just like a full. I mean, the oh yeah. The difference between this is once you've found a 9, you're done. You've like you add it to your list, and then you're done with like that path. The DFS all is you just want to. You're counting all the paths, right? The first one was is like how many zeros get to 9s, and the second one is how many total are there. There could be multiple 0 to 9s, and so you have to increment it. Okay, I mean if you're doing the DFS, so what this seems to suggest is you can solve this with DFS. The state space is small enough that you can solve it with DFS. Since all the moves have a cost 1, Dijkstra's queue keeps itself sorted by default, so we can use a DQ within sort. Okay, so it uses a DQ as opposed to min heap. I mean, I used A star, but that is technically true. If the cost is only ever 1, you can just use a DQ because like you're always adding higher costs at the end, lower costs. Actually, is that the case? Because you're popping off lower costs, but then that lower cost may produce a slightly higher cost that needs to go somewhere in. So I actually don't know if that's the case. I'd have to think about that more. Use Dijkstra from it is way faster to search from the back, meaning drop every byte, then reverse the drop and check Dijkstra's. Interesting. Also, when the cost is uniform, just do a BFS. Yeah, see, I don't think this is actually the case. You want to prefer. I can do the BFS later and check, but I don't know that this is the case. How about this? Is Dijkstra with uniform cost just a BFS? No. While similar in construct, Dijkstra algorithm with uniform cost is not exactly as BFS. BFS explores nodes level by little, considering all nodes at a given distance from the starting point, whereas Dijkstra's prioritizes visiting nodes with the lowest cumulative cost. Yeah, see, I don't. Maybe they're saying it wrong. It's potentially a DFS, but I don't. Maybe that's where it's wrong. Anyway, Rust and Python. Port of my earlier Python solution in Rust. Part 1 BFS, Part 2 binary search, starting from 1024. Yeah, that's cool. Sounds like a lot of people thought of the binary search, which that did not come to my mind. I guess maybe I just breezed through it again because I was doing brute force, but definitely a solution to that. Tomorrow will probably be more challenging. Yeah, you just don't know what's coming, right? Today was an easier day, I think, for most people on average. especially if you've done the previous days, right? So if you've done day 16 and you probably say to yourself, "Oh, this is easy. I've figured out how to do 16. I can do the same because this one is the space is smaller and easier." So, um can't be bothered at this point. I mean, I do want to do the binary search because I think it'd be fun to see how much it ekes out of it. Part 2 runs in 2 milliseconds. That's really good. Did not implement a binary search, but instead did a tweak that I see some others have done too, but most second part of the automation. We keep track of the shortest path, and only when the new bytes hit this, we need to do something. Okay, yeah. So that's what the previous person was talking about, which I didn't think about. So there's actually a few ways to solve this last one. Brute force it. Only recalculate Dijkstras when you've like hit a node that breaks your shortest path, and then or hit a corrupted node, and then just do a binary search of the tree. It'd be interesting to see which one is faster. But again, I think all of them probably, especially if you use like parallelization, all of them get you there way under the, you know, time for like solving. There is no official time for solving, but I think Eric has said before that the the guy who made this stuff is that like all the solutions should he designs all of them so that there's a relatively efficient solution, and by relative he means you know any hardware in the last 10 years should be able to solve it in the last in like within seconds and not minutes. Something along those lines is what he said. So network X library, is this a Python thing that I just don't know? Have I looked at this before? Network X, is it just like it implements all the tools for you, Dijkstras and stuff like that? Release documentation. Tutorial. Create a graph. Nodes, edges, elements. I think I've used these type of things before in other ones. I don't know if I've used Network X, but I've used this in other problems. Yeah. Okay, this is just a graphing library. So yeah, much like the pathfinding library, again, there's like tools like this that if you say, "Oh, I want to be helpful. I want to like this is particularly useful in like your career or your job." It's good to know how A Star and Dijkstra and Floyd Warshall and all these other ones work. All these graph algorithms. You want to know how they work and where they're useful. But to implement them yourself is not always necessary, right? And so if there's some really popular library, like I presume Network X is, learning that library is also important, especially if you want to go into a field where that graphing is important. So, social networking type things. I mean, you can use graphing all over the place, so probably just knowing it in general is good. Just A star all the way around. Yeah, that's perfect. These are all really good. Okay, so maybe it looks like it's just a. He did use A star. Yeah. So yeah, this is a good performance tweak. You could just, I think this is a great summary of like what you could do. Is like we've talked about before, right? Uh, Talks about these other performance tweaks. So yeah, good. Jupyter Notebook. Oh, that's cool. He has a notebook. Sometimes this is fun because you can see all of how they do it, which is especially nice, right? You know what they're doing and how they're doing them. This is a lot of code. Binary search, get factors. Oh, this is all of the days. Wow. cool. That's kind of fun that you have your whole thing in a single Jupyter notebook. uh, yeah, I've like whenever I've done some algorithm classes or like AI classes and stuff like that, they often use Jupyter notebooks, and I've not done it on Windows, but I've like set up my own Jupyter notebook server so that I can keep track of all my notes and stuff. Obviously, Google Colab is a cool way to do that, but that's kind of cool. That's a cool way to solve these problems and then have them available to you at any time, especially considering like, oh, and sharing them, right? I just share them on Gists. So okay, it sounds like there's a couple optimizations that you can do besides just using par iter and heating up your office. Um, but so maybe we'll in a recap we'll solve those. We'll try and update our solutions to do those and have a peek at those and see what they look like. But otherwise, it was pretty easy day. Nothing too crazy. Hopefully, you had a good time solving it, especially if you've done days before. It probably wasn't too bad for you. We'll see you back for tomorrow.